Commencing countdown.
3, 2, 1.
This is the Contracting Experience, connecting government contracting professionals to the world around them through conversations with acquisition influencers, insights into evolving hot topics, and sharing lessons learned from the field.
In this episode, we are featuring another great podcast within Air Force Materiel Command. It is Air Force Lifecycle Management's podcast, AFLCMC Leadership Log podcast. The podcast has over 70 episodes and includes a variety of topics like what's happening at the Rapid Sustainment Office, civilian developmental education, cyber resiliency, and perspectives from Air Force leadership. In this episode, we feature the Leadership Logs episode number 40 on digital engineering. It is important for acquisition professionals to understand what digital engineering is and how the Air Force can use it, and this episode does a great job of breaking it down in an easy and understandable way. When you're done listening, go check out the AFLCMC Leadership Log podcast on your favorite podcasting app or at the Divids link in the show notes.
Gentlemen, thanks for joining us today on Leadership Log, which is a podcast for the Air Force Lifecycle Management Center community on topics of interest. And today we want to learn a little something about digital engineering. It's a term that everybody talks about. Not too sure that everybody understands it. And so I know you gentlemen do, and you're going to explain it to us. So we'll start. You could just introduce yourself and give us a little background on your career. We'll start with Lieutenant Colonel Locklear.
Hi, thanks for allowing us to be here. This is going to be a lot of fun. My name is Jameson Locklear. I go by Heater, and so that may slip out during the meeting. I'm the Deputy Program Manager for the ET7A Red Hawk program, which is the advanced pilot training program that is replacing the T-38 Charlie within Air Education and Training Command. This is a really exciting time for me to be a part of the program. My last program was the KC-46 program, where I had the pleasure of working with your other guest, Mr. Joe Baker. Before that, I spent some time within AFMC, and then before that, I was an intelligence officer at Shaw Air Force Base, where I got to meet a lot of pilots who flew on the T-38, and who subsequently would be flying on the T-7. So I'm pretty passionate about providing them the best training opportunity that they can. And I'm happy to be here talking with you about digital engineering. Thanks.
All right, great. And we'll go to Mr. Baker.
Hi, my name is Joe Baker. I am currently the Director of Engineering for the Mobility and Training Aircraft MATAC Directorate. As Lieutenant Colonel Locklear said, my previous job was as the Chief Engineer in the KC-46 Program Office. I've also been in the Air Force Research Laboratory, both as a branch chief and as Deputy Capability Lead for Agile Combat Support. Before then, I was a Program Office Engineer in the Global Hawk, the C-17, and T-6. Looking forward to our conversation.
All right, great. So we're going to start at the top. Again, like I said, we want to talk about digital engineering, specifically how it relates to the ET7A. But I want to start with the basics. So could you, Mr. Baker, could you explain to us how is digital engineering different from our current engineering approach?
First, digital engineering is not changing the engineering approach. It is providing new tools for the engineers to do their job better and faster. For example, my son is a junior in high school, and we're about to start the college visits. And when I went on my college tour trips, if I wanted something to read, I had to bring a stack of books with me. If I wanted music to listen to, I brought my tapes or my CDs. For navigation purposes, we had paper maps. If anyone remembers TripTiks from AAA. Any games we had were those, the handheld things that are, 8-bit pixels or even board games at times. Didn't have an option for watching TVs and movies. Cell phones were basic, rudimentary, first-generation cell phones. And then the schools I was going to, I had pamphlets. And maybe if I knew somebody from that school, their stories, but I really didn't know much about the school. So today, everything I want is on my smartphone or on my tablet. I've digitized my books. I've got streaming services for movies, television, music. Navigation, I now have GPS with oral cues as opposed to trying to look at a map while I'm driving. Obviously we've got instant coverage. Every place I want to go, I can be in contact with anybody through text or voice. And then, before I even think about going to a school today, I can look it up online and I can get a virtual tour. I can read bios of professors. I can do all these things. So digital engineering is sort of the same thing. I'm still going to be doing the same engineering tasks I have today, but I'm going to have far better tools. I'll be able to understand my weapon system better. I'll be able to iterate on changes and really fine tune the weapon system long before we start, quote unquote, bending metal or moving from the digital world into the physical world. So a lot of people think digital engineering is nothing more than working on a computer or getting your deliverables in a PDF as opposed to a stack of papers. And that's just not the case.
Those are some great examples. It also reminded me how old I am, but either way. So I say, I'm a journalism major, and so I think of everything in terms of reference books. Trying to cite a source and to cut and paste text is just much simpler than having to retype it. It's kind of a simple example, but some of the examples you talked about are a lot more powerful. What are some of the advantages that digital engineering can offer? So you talk about new tools. What capabilities can that bring then?
So using your reference book as a vignette. So let's say I was writing a book or a paper on Air Force engineering, the history of Air Force engineering, much like I'm designing a weapon system. So the first thing I do when I'm designing a weapon system is lay out what are my requirements? What is this thing supposed to do? We call it the reference architecture. What is it? What isn't it? So going to the book example, if I'm writing a history of Air Force engineering, that's a very broad subject. So I'd need to narrow that down. Am I going all the way back to Signal Corps? Am I going, to the World War II period, or is it just 1947 on? Am I interested in just the engineers at Wright-Patt? Am I interested in the engineers across the enterprise? Maybe just the engineers at the test center. So I'd have to define that architecture. The next thing that I would do in the reference book is under a digital engineering sort of tool set, the system, the automated system, would find reference books for me. Instead of going to the library and spending hours poring over books, trying to find ones that have interesting information to my reference architecture, to my boundary conditions, it would go in and find those reference books for me. And not only that, as the tools mature a little bit more, it will identify the sections in the books that meet my reference architecture. So if I've got a history of Wright-Patterson Air Force Base, for example, is one of the reference books, it'll say, chapter 3 and then 5.2 and 7 have engineering references in it. So that will save me time in gathering my information to write my paper. Just like in designing an aircraft, it'll go through and the digital tools will help me shape it. They will help me understand how the various subsystems are going to play in, how the avionics are going to work together, what avionics I want to choose, what particular LRUs do I want to choose, where do I want to place my antenna, and then iterate on that. So I will have candidate designs that I can actually test. Now, when it comes to the paper, I still have to write my paper. We're not talking about artificial intelligence here that's going to write the paper for me. I have to pick which of these sections that the digital tool has identified as being applicable. And I have to pick the ones that really are appropriate for the paper that I'm writing. And then I have to physically sit at my keyboard and type my paper out. Much like in the digital world, at some point I actually have to build that airplane. Once I've got my paper written, now the digital tools can help me out again. So the tools can, today we can spell check. And the spell checker is not even that great. Principal versus principal.
Right.
A digital tool, an appropriate digital tool, will not only do a proper spell check, it will also go through and check it for grammar, check for readability, check for consistency, make sure I've got everything in the right place and I'm not bouncing between, Vietnam era engineering and, Reagan era engineering. Not, make sure it follows a linear flow. It can recommend changes for me. If, let's say, it's a paper and I've got a 5-page limit for whatever reason, and I've written 8 pages because I've got so much good stuff, it can recommend to me, okay, reduce this, take these things out, condense this part, and you can get down to 5 pages. Mm-hmm. Once that's done, then the tool can also publish for me. It can push it out to, if I'm in school, push it to the professor. If it's something I'm doing more as an exercise for myself, maybe it can publish it on any one of the online publishing tools.
Right.
Much like when you get to the digital enterprise, yes, I've got to build this thing, but I can also test that airplane long before I start bending metal. I can test the subsystems. I can test the components. I can make sure they're all working together. Make sure I don't have interference in my communications paths. I don't have frequencies stepping on each other. I don't have physical interface interferences. So that when I'm putting the airplane together, I know that my holes are going to line up. I know that I'm not going to have 2 pieces bumping into each other because I have a mistake in my CAD drawings. I'll know all of that. So I'm still doing engineering. I'm still have to think. I still have to make engineering calls, engineering judgment. But I've got all of these new tools that'll make it easier for me to do that. And once we've done that, as Lieutenant Colonel Locklear is going to talk about with the T7, I can start building, and I'll start building faster. I can start testing, and I can cut out a lot of build-up points, or a lot of points that aren't going to provide me any useful information. So that's where the power of the digital engineering is going to come into play. And Lieutenant Colonel Locklear, I think, is going to provide you some specific examples from the ET7.
Yes, sir. So thanks, sir. Let's draw this into the real example of the ET7. So Lieutenant Colonel Locklear, if you could, how is digital engineering equating into this?
Yeah, thanks for that. I really appreciated Mr. Baker's breakdown of the history of engineering and how that could apply to the digital model, because I think that is a good metaphor. And I'll preface what I say about the ET7 by saying that we are a digital pathfinder. And so part of that means we're doing stuff, and part of it means we can see what could be done. And we're maybe not going to be able to do all of the things that we know could be done. And I'll give examples of both of those things. But the first thing that happened as part of the program was that our prime contractor, who's Boeing, was able to go to final draft of the aircraft to flying the aircraft in 3 years. And that is unprecedented for the Boeing company in the digital age. That is something that they had not been able to do previously, especially not for an aircraft that is as complex as the ET7 is. So they have 2 aircraft right now that we refer to as T1 and T2, and these are jets that Boeing built to do some initial test efforts to buy down some of the risk later in the program. We're going to do a lot of testing on other prototypes of the aircraft, but these 2 are going to let us get some early learning and move on to later stages of the test program. But that was able to happen primarily due to digital engineering. They were able to design with such tight tolerances on every part that they did something very close to full-size determinate assembly. What that means is that when the part shows up from one supplier and another part shows up from another supplier, both of them come together and they just click into place. There's no shim required. There's no design change required to meet those parts, to get those parts to meet together. They just show up and then they click together. That is a significant reduction in integration time at the Boeing factory. So they can get a fuselage from Saab in Sweden and then just piece it together with other parts that either the Boeing company made or other suppliers made. That reduces the amount of people that are in the factory, so that saves money, and it reduces the amount of time significantly. So T1 and T2 are entirely shimless. So I personally have never built an airplane. I have built pieces of furniture, and I couldn't say that any piece of furniture that I've ever built is devoid of shim, or it's just not flat or square or anything like that. That's the other way you could do it. No shims, but it's not square either. So the idea that they were able to design digitally this aircraft and get those pieces together without having to adjust anything. And some of these pieces are, a dozen feet long or longer, and they're just arriving and then, putting them together in a jig. And that's amazing, amazing to me. And we haven't even gotten into the production of this aircraft at a large scale. Once we get into that phase of the program, they're going to be able to use this design method to pump out aircraft at a very high rate of speed, which is pretty phenomenal. So that's the thing that has happened already on the program. We've already taken advantage of that design effort that Boeing did, and I personally think that that's pretty phenomenal. Some of the stuff that we're going to do is take some of the verification of the design, specifically when it comes to support equipment or technical orders verification, and we're going to put that into a digital environment. We did an assessment of all of the verification efforts that we have to do within the technical orders, which is essentially the manual. So the manual that you get with your car has a bunch of stuff that says to do, if this happens, do this. Well, we have to verify that for the aircraft. And so we have to put a lot of time and effort into that, usually on the aircraft. So you're just crawling around the aircraft and pulling stuff apart, putting it back together. But our team came up with a way to take about 10% of that effort and move it into the virtual environment. And so that's going to allow them to do it when the aircraft isn't available because it's being flown or something else is happening to it, which is an amazing cost savings in terms of time. That is another Pathfinder effort. So on our program, we're only going to get to about 10% of the overall verification of those manuals happening in the virtual environment. But in subsequent programs, we could see a significant increase in that amount. I don't know that I can see in my mind's eye 100% verification in the virtual environment, but I can see us getting very close to that and making pointed checks of the physical environment to make sure that the model is correct. But that's something that we are doing. We're going to take credit for that. There's other activities that we're doing throughout the life cycle of this development effort that we're going to push to test. So when we get to test effort, when we get to specification verification, which is the reference architecture that Mr. Baker was talking about, once we get to the stage of the program where we have to say, yes, this training system is doing what it's supposed to, we're going to pull as much of that into the digital environment that we can. Right now, we're still early in that, and so I don't have a projection of what percentage we're going to be able to do that for. But some of the models that Boeing has are going to enable our team to pull some of that out of the physical world and into the virtual world, and that's going to be pretty incredible.
So I can see some definite advantages. I mean, just off the bat for like maintenance alone, that maintainers will have, if they need to replace a panel on a wing or something like that, they could pull one off the shelf and it's going to fit, as it was intended to do. What are some other, just looking at it from a maintenance standpoint, improvements that you could see there?
Yeah, so this is one of those things where I can tell you where we are, and I can tell you where the state of the art is going. So where we are right now is that I have a 3D model of the entire aircraft, and that 3D model is accurate. And so when we are learning about specific parts, like if a specific part has a problem, and that problem is occurring more frequently than we would have expected, we can use that 3D model to understand what we need to change about the design. And because of the way that it is linked, we should be able to roll in any other required design changes much faster than we normally would. Where we're going is a single thread model. So I can start at one point of the aircraft, and I can follow that single thread all the way through every single part throughout that 3D model. And then I can use that model to run through cycles to determine what are the pieces and parts that are gonna break first, so that I know predictively, this is the piece that is gonna break first. And I can either redesign that piece so that it doesn't break first, or maybe it's really cheap. And so I just say, all right, this is going to be our LIMFAC. We'll just buy a bunch of those and replace them out as needed. But we're able to make a really precise decision on that, and using predictive analytics in a way that is possible, but it's very hard today. We're going to be able to do that easier and faster in the future.
And there's definitely a cost savings for that, because now you can schedule a maintenance repair for at the time of your choosing, not having to wait until the plane breaks and then fix it.
Right, and not calendar based, right? I'm not saying, well, this aircraft has flown this number of weeks or this number of flight hours, so take it in and get it worked on. I'm able to say, well, each of these parts are at different stages, and so this is what the model should predict for taking it in. And there's also a thing called a digital twin, and so eventually, this is not something that our program is planned to get to at the current stage, but is possible, where each aircraft, so let's say there's an aircraft that's got Mr. Joe Baker's name on it, that specific aircraft would also have a model, and that model would be the exact same aircraft, but in the virtual world. So like every time you updated a piece of Mr. Joe Baker's aircraft, it would get reflected in the digital model. And so then you're able to not only precisely predict fleet maintenance, but you are predicting individual aircraft maintenance in a way that wasn't possible previously.
That's really cool. So talk to us, give us the status. What's the current development on the ET7? How is it going?
Yeah, it's going well. We are in the build and test phase of the build, test, field model. So right now, Boeing is building with their suppliers 5 aircraft that we call APT, Advanced Pilot Trainer 1 through 5. And those are going to be the aircraft that we do government testing on. Additionally, they're building the training devices that are part of the Advanced Pilot Training System constellation. So a lot of the digital engineering effort has been focused on the aircraft, but this system involves a lot of effort put into the training devices, which are a simulator. If you've ever flown in a flight simulator, it's that type of thing, but this would be at a level that we haven't achieved previously. And the visual acuity involved is pretty phenomenal. So there should be some training that the Air Education and Training Command team should be able to do in this level of simulator that they weren't able to do previously. And so that should be pretty neat. So right now we're building the aircraft. We're doing some risk testing that Boeing is doing on their own, and we're involved. And then starting at the end of this calendar year, early next calendar year, we'll be doing government-led testing, primarily out at Edwards Air Force Base, but also at other sites for different aspects of the testing. And that will let us know whether or not the aircraft is ready for us to buy more and make a production decision. And then we'll transition into fielding. And we're several years out from that, but that's operating with the end in mind. So we're testing the aircraft so that we can make sure that we're there when ready to make that production decision.
And now this was an aircraft that we needed to train pilots to fly supersonic aircraft, primarily, I guess, because there's not two-seater versions of the F-22 or F-35. And so you needed a trainer aircraft that would prepare pilots for those aircraft. Is that correct? Or
that's definitely part of it. So fourth and fifth generation aircraft in general are expensive to fly. And there are some training events that you just frankly don't need to fly an F-35 to fully grasp, or an F-22 to fully grasp. You could fly them in an aircraft that handles similarly and save a lot of training time and cost, especially if instead of doing it at the very end of your training profile, you're able to do it earlier in your training that AETC runs. So right now, the T-38 takes people from flying their initial pilot training into the fighter track. And so they're able to start moving to the fighter bomber track with the T-38 Charlie, but then they have to go do a lot of training in the formal training unit at the end, where they're in an F-16, they're in an F-15, they're in an F-22, an A-10, an F-35. And we think that based on the T-7's design, we should be able to move some amount of that training from the formal training unit back into the spot held by the T-38 right now. And the T-38 it wasn't designed to do that. It was designed 60 years ago. And there have been some updates that have made it better, but it's still not going to get there to the level that it would need to be to really pull that training back. But the T-7 should allow us to replicate the training of a fourth and fifth generation aircraft at a much higher fidelity, and allow us to do more of that training earlier, so that when our pilots get into their formal training unit for the F-22, they are more prepared. They spend less time in that training school, and they're able to get out to the combat air force as quickly as possible.
Okay. And what are some other kind of basic capabilities that this aircraft brings, new capabilities it brings to the warfighter?
Yeah. So a lot of it is integration with the training devices. So we should have a high fidelity ability to fly on the ground, in the simulator, and in an aircraft within the same sortie. So both the person in the air and the person on the ground would virtually be linked and would be able to operate at a very high fidelity. And so that's a pretty unique capability. There's a lot you can do there when you start thinking about flying in a formation and understanding proximity to aircraft. Obviously, the person in the plane, if they looked to their right, wouldn't see an aircraft there. But if you're flying in the simulator, they could put that visualization on the screen and you would get that feeling of doing that. So that's a pretty significant capability. And the safety as well as power of this aircraft is what is really going to take it a step up from the T-38. We're working on a new escape system for the aircrew members that is in testing right now. And that, coupled with the overall integrated design of the aircraft, should make it a safer aircraft to fly. And safety is super important in the student environment because these are our least experienced aircrew members. And so we want to make sure that any safety choice that we can make in the design, we do, so that we can provide them the best opportunity to learn.
Mm-hmm. So you mentioned a little bit on simulators, but how are the rest of the items that support the aircraft going? And does digital engineering help in that regard too? I mean, if you're going to build like a ramp that goes up to the door, it'd be great if it actually made it all the way to the door. So
yes. So like Mr. Baker mentioned, the same activities that our systems engineers would be doing, in a non-digital world, they're doing in the digital world. So they still have to make sure that all of the spaces align and are able to connect one piece to another, specifically with support equipment and other on-the-ground devices. But the models that we're getting for support equipment will be high-fidelity models. I don't know that we have seen the same level of schedule reduction in the design of support equipment that we did in the aircraft. But we were able to work with Boeing to utilize as much common support equipment, so support equipment that we're already using in the Air Force. So we try to minimize the amount of peculiar support equipment, so the stuff that is only going to get used on the T7. So it's possible that digital engineering helped with that, but it was not at the same level as some of the other advances on this program.
So we're just about to the end of our time, and I appreciate how you've broken this down and help us relate better to get a better understanding of what digital engineering means. If you could, is there anything that we've left out or anything that you'd like to add? We'll go back to you, Mr. Baker. Anything else you want to add?
Yes, Daryl. One thing that we haven't talked about already is that these tools are far more powerful than we're used to working today. So there is a digital campaign within the command that is looking into what does it take to migrate us to this full digital environment. One of the big things that they're really looking at is what is our IT infrastructure needs. I think it's an open secret that we do have some limitations that we need to overcome in order to start using these powerful tools. We certainly need to be able to interface, as we've learned working remotely over the last year, interface using these powerful tools remotely. So my contractor who may be across the country and I, or in Colonel Locklear's case in St. Louis, that we can work together seamlessly as if we're sitting right next to each other. So we are exploring those requirements to make that happen. We're looking at policy and even up to law. Is there anything that prevents us from doing this that we can change or need to change? And then obviously training. You provide a bunch of people a whole bunch of new tools. You can't just throw it at people and say, here, have fun. We do need to understand what it takes to train not only the engineering staff, but the program management staff, the contracting, finance. As Lieutenant Colonel Locklear was saying, as they're designing and testing an airplane virtually. we're used to a very linear approach to weapon systems. I've got a paper design, I start bending metal, I go test. I can measure my progress very easily that way. Measuring progress in a digital environment is a different thing that we're going to have to learn. So these are all things that this digital campaign is looking into, working on to help us make this change. And don't get me wrong, we are going to make this change. Our industry counterparts are moving in that direction. Some of the non-traditional DoD contractors are already there. Mm-hmm. And so we have to move with them, or we just aren't going to be able to keep up.
And Lieutenant Colonel Locklear, anything you want to add in?
Just to piggyback on that, I think that the pathfinding efforts of our program, coupled with AFMC's digital campaign, are going to move the ball to where it needs to get to. But it's really going to be a mindset shift that will happen, and not necessarily a bunch of discrete tasks, because like Mr. Baker mentioned, we're already in catch-up mode. And so by the time we catch up, we're going to need to catch up again. And so essentially the mindset shift is that we are constantly looking for the state of the art and what is the best way for us to utilize the minds that we have within the command to produce a product and an end item for the warfighters and the trainers of those warfighters. So that, I think the mindset shift is the thing that we're working on the most right now, and that will pay the biggest dividends in a 5 to 10 year time frame. Thanks.
So, gentlemen, thanks very much for joining us today. I think you've been very helpful in understanding this topic better. And I think it's probably something that we're going to have to come back and address again in the future. So thanks again.
Thank you, Daryl.
Thank you.
If you have suggestions for topics or people to interview or feedback on the podcast, you can submit those at thecontractingexperience@gmail.com. I want to thank you all for listening to the Contracting Experience podcast. Until next time, keep connecting to the world around you.